All right, so this is roughly sum of like 6 through 12 and 16.1. So what they want me to do is estimate the sign of this integral, right? Where they tell me that D is the unit disk. I think in the book they actually say the inside of the unit circle, right? So that's circle of radius 1 filled in with the edge. Cool? All right, and then B is the bottom of the unit disk, and R is the right half of the bottom half, I suppose. Okay. Now I'm supposed to be applying this integral to this function 5x, right? Okay. What the hell does the function 5x look like?
Straight line, slope 5.
Ah, there's a problem.
It's three-dimensional.
Good.
Isn't it?
So if I wrote f of x is 5x, I would really like you to think a line with slope 5, right? So that's over 1 unit, up 5 units, x and 1, right?
So there's a z. Is that
You
good?
guys with me on that? But this thing is living in 3D land.
So the z's are going to go off into infinity.
So this is f of x and y is 5x plus 0y, how about? Right? Which is what kind of object?
Plane,
Yeah, this is a plane. You guys see that?
because it flies off.
So you could think about this thing as like, okay, so the y's, there aren't any y's, right? So this is some kind of maybe a cylinder, right? So I told you that cylinders get made when you don't have one of the variables specified. You guys with me on that? So this would be a cylinder made out of that.
So it'd be closed on the end then? If it's a plane, it would be like an open cylinder?
So it looked like this, right? Like here's your line, and this one's going to be z equals 5x, right? So there's your z-axis, here's your x-axis, but you need to push a y-axis out of the board, right? And so you get this funky plane, right? If you slice at y is 0, it is the line z equals 5x. But if you slice at the plane y equals 1, then it's still the line y or z equals 5x, but it happens at y equals 1. So that line gets swept forwards and backwards, right? So it's kind of a linear cylinder. You guys remember that? Okay, so when they're asking for, when I add up the area under this thing over the unit disk, right? So that's, there's this plane, right? Here's your x-axis and your z-axis, right? Oops, sorry, let me do that this way. Y-axis. And there's your x-axis, right? You guys with me on this picture? Okay, where's the unit disk?
It'd be like an ellipse around that plane.
So that D lives in the domain, right? You guys see that? You're integrating over something, that something lives in the domain. So that's a disk, right, in the xy plane. And then there's some volume underneath that thing. You guys see that?
Why would it be disk and not, if the plane's in 3D, why would it not be like a 3D ellipse there?
Yeah, why wouldn't it be a three-dimensional thing?
Yeah.
Because so what I'm really doing here with this thing, right, is I'm thinking to myself, okay, there's some region, that's my disk, in the XY plane. And then there's some function over the top of this. It doesn't matter what the heck it is, right? But if you're integrating over some region a function g of x and y, d area, right? This thing says slice d up in little areas, right? This thing says add those up. And this guy says with these as heights.
And the height would be in the z direction then?
Yeah, so the height's the z direction. So what you're going to do is you're going to take your domain you're integrating over. You're going to cut it up into lots of little bits and bobs. Right, so we're going to take our disk and we're going to chunk it up. Right, so I cut it into little x and y slices, right? And one of these little slices might be this one here, right? Where's that little thing live? Well, it lives back over there someplace. I drew that picture way too small. Let me blow up my circle here a little bit. Okay, so I have my, it's not a good looking disk. So I have my disk in the XY plane, right? And so there's some little prism here. And on that prism, or above that thing, there's some little bit of this blue plane, right? And what I'm doing is I'm taking the heights there, multiplying by the area of the base, and then adding up a bunch of these. You guys see that? What's special about this one is that I'm integrating over D, right? Which goes, well, really, on both sides, right? Equally on the y-axis. And this function is positive on the right-hand side and negative on the left-hand side by the same amounts. You guys see that? Even, right? With respect to, well, something. Cool? And so what I'm going to get is these two little slices of cheese. You guys see the little cheese slices?
Yeah.
Right, this is like a little wheel of cheese, and then you cut it. Right? So there's this funny little wedge over here, and there's a funny little wedge over here. Those are the same size wedges, right? Except that this one gets counted as negative, and that one gets counted as positive.
So it'd be 0 then?
Yeah, so this would be 0. You guys see that? And that's really, and I said even earlier, I really should have said odd, because 5x is odd. You guys remember that? If you integrate an odd function over a region that's symmetrical with respect to 0, you get 0 out. Okay, now how about the bottom? If I integrate this over the bottom half, right, that's where y is negative. In this picture, that's the kind of back half. What's that going to be?
Exact same, because there's no change in x.
Yeah, that's-
Changes in its difference in y's being taken out.
You guys see that? We haven't really changed this picture at all, right? We still have x's that are positive and x's that are negative in the kind of same picture, right? So we're going to get half wedges, right? But there's still a positive one and a negative one, so this guy's still going to be 0. And again, that's because 5x is odd and we're integrating over a symmetrical region with respect to the y-axis. So how about this thing? Over the right-hand side, that's when x is,
That'd be the positive direction of x?
that'd be the positive side, right? So now I really have discounted one of these sides, right? I've really discounted this whole bit. So now our wedges,
Are entirely positive.
yeah, our little prisms all have positive heights. Some of them are small, right? The ones towards the y-axis are short. The ones out away from the y-axis are fairly tall.
It's almost like a shadow.
You guys see that?
Mhm.
But it's just a little wedge of cheese. It's going to have some volume enclosed in it, so this is going to be positive at the very least. We could give a good overestimate for it. What would the dumbest overestimate be?
One.
That's an
Close, yeah, right? The x values go up to 1, right? So if the x values go up to 1, how high does it get? 5, right? Because the function that you're integrating is 5 times the x's. So you pick the biggest x, that's 1. So the highest this thing ever gets is 5. And then how big is the area of it?
Does this-
Divided by 2.
Divided by 2.
Would be a triangle.
It's a half.
What half pi r squared? I mean,
Yeah,
Yeah, R is 1.
yeah, r is 1. So I think you need a pi in there too.
I said pi divided by 2.
Oh, pi divided by 2. Yeah, 5 times pi over 2. You guys see that? Like, that's a good overestimate. You guys cool with this? So I know that this is positive because it's always, the heights are always bigger than, I'm sorry, the heights are always at least 0, right? And some of them are definitely bigger than 0, so there is going to be some volume in there. But I know it's strictly positive. And I know it's smaller than this. How do I know it's definitely strictly smaller than this?
because they would all have to be the maximum value, and we already know it's on a curve.
Yeah, exactly. Right? I know it's not flat across the top. I know it slices in.
Right? We actually assume dividing by 2 gives us the, well, actually, it can be.
So the pi over 2 gives you the area of the base, and then we took the highest height. Right? So that would be assuming it's actually a little cylinder with this as the base. But I know it's not because I know that plane slices. You guys cool with this? That kind of makes sense? Picture's horrible. Cool?